Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do. But only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field. Sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. My guest today is Leor Weinberger. He's the director of the Gladstone Center for Cell Circuitry, UCSF. He's the William and Ute Bose Distinguished Professor there. And we're going to talk about a novel treatment that slashes HIV up to 10,000-fold in monkeys with a single dose. So it sounds very promising. So welcome.
Thank you, Richard.
Yeah, if you would tell me a bit about your background and how you got to study this in the first place.
Sure. I grew up in Toronto in Canada, and my family was always engineering focused and science focused, and I got interested in the sciences at a very early age. And we moved down to Washington, D.C. when I was in high school, and I got exposure to the U.S. system and went to college in the U.S. and understood that you could study many different things, which is very different than the Canadian system. And so I started off studying biology because I thought biology was interesting.
Right.
Very quickly realized that I really had a way of approaching problems that was more like physics, and that where my family intellectual tradition came from. And so I took on physics as a major and went down that path and started studying. At the time, there were many physicists who were transitioning into biology in the 1990s, and I caught that same bug, went to graduate school at Berkeley and studying biophysics. And the particular branch of biophysics that I was studying was theoretical biophysics. There were a few individuals in the field who were studying viruses and particularly using models from mathematical biology and epidemiology to apply to viral kinetics inside of patients, in HIV patients. So this was in the 1990s. There were a group of physicists that were transitioning into biology, largely solid-state matter physicists, condensed matter physicists, using the mathematical tools of that field to apply to biology and try and approach biology in a more quantitative manner. And I caught that same bug and started studying with those physicists/mathematical biologists. And there were a group of them who were working with infectious disease specialists, virologists on HIV. This was at Los Alamos National Lab in New Mexico. I went to work with that group and really got excited and interested in using those models to understand the dynamics of the virus. And there were a number of really important discoveries and insights that were made during that time using these quantitative models. And then I continued moving out west to Berkeley for graduate school in biophysics and continued studying this field of quantitative or theoretical biophysics on particular viruses and HIV, and spent my graduate training really diving into the molecular biology of the virus of HIV, utilizing these same mathematical models, but at a lower scale of biology, the molecular scale, instead of the cellular and plasma scale that had been used before.
So what have you discovered about viruses and viral action that applies to HIV? Let's move forward to that story.
Sure. In particular, this story that just came out, or are you still asking about the background?
This story that came out, yeah. I understand your back studies and everything. So, right. About HIV, how did you start studying it and what did you find?
So I started studying this in graduate school, actually. This was an idea that's 20 years in the making because of these mathematical models. One of the problems we had in the field, even over 20 years ago, was that you put a patient on drugs, on antiretroviral drugs, which are very effective. They're safe and they're effective. However, they don't cure the patient. We don't have a curative therapy for HIV because the virus goes into a long-lived dormant state that we call latency, proviral latency. And when a patient discontinues their drug therapy or stops taking their antiretroviral therapy regimen, within 1 to 3 weeks, the virus rebounds back to pretreatment levels. And this happens in virtually every patient that discontinuation has ever been tried in. So the virus comes back from this dormant or latent state, rebounds, reverses its latent state. And this is the problem that we faced.
When you apply a certain drug to someone that has HIV, the HIV goes into a latent state. And then after, I would guess there's some, maybe quorum sensing from the virions or, maybe using the cell senome, they're able to sense and then come out of a latent state after a few weeks. Is that right?
That was one original hypothesis. That's not what we believe happens. And it's been pretty well established that what's going on, in fact, and this is the subject of my graduate work, the virus establishes a very early infection right after the patient's infected or the animal's infected, establishes a later reservoir, cells that are dormant, not actively replicating or transcribing the virus. And those cells are sitting silent. They're latent. Those cells are not attacked, quote unquote, by the drugs. All the drugs that we have attack or target enzymes of the virus. And the viral enzymes are only created when the virus is active at replicating, transcribing. So they don't exist in these latent cells, and these drugs really don't have any effect on the latent virus because there's no enzymes for them to target. Does that make sense?
Okay.
Those latent cells are there pre-existing. The drugs clear all the actively replicating virus, and the only thing that's left is the silent or latent or dormant virus. And when you remove the drugs, these latent cells that are probably always continually, spontaneously reversing latency.
Why wouldn't there be? In fact, cells produce exosomes all the time.
Right.
Take them in and put them out. So I would think there would be some form of quorum sensing amongst virus cells, cells affected with viruses. If you take out the ones that are actively producing virions, then there's no exosomes from them that would go into latent cells, and maybe there's an absence of signaling. Therefore, those cells now activate, but the signaling changes.
It's an interesting hypothesis. I don't have any evidence for that. But one thing to remember is that these latent cells, these dormant cells, they don't have any biomarkers that distinguish them from regular cells. All that's happened is that the virus has integrated its DNA, its proviral DNA after reverse transcription, into the host DNA randomly, pseudo-randomly.
Are there any, what's the method of entry for HIV? Are there any capsids, empty capsids that are still attached to the outer cell membrane? Or do they, like a T4, does it go in like that?
It goes in through the CD4 receptor, but the CD4 receptor is present on all CD4 cells.
It pulls in the entire capsid as well as the payload of the virion, right?
It pulls in everything, and there are very few virions that infect a cell. There's one, these latent cells comprise a very small number of the total number of cells, a total number of CD4 cells, probably 1 in a million, 1 in 10 million. And there are very few of these virion particles that infect an individual cell. It's probably one virion for every few thousand or more cells. So it's not like we have a lot of these virions decorating the cell. It's a single viral particle per cell that's infected. And there's really nothing distinguishing these cells, these latent cells, from a regular cell. There's no active viral replication or transcription. These cells are just carrying the viral genome somewhere in their genome that's silent and hibernating. So it's not like there's anything going on in these cells that distinguishes them.
Have you looked at, again, exosome production? I know it's hard to isolate these things, but I know in tumor cells, they've seen a change in the extracellular vesicle profile.
Yeah, tumor cells are different. Tumor cells, right, they're transformed. But regardless, it has been looked for 20 plus years. Biomarkers for HIV latency have been looked at for 20 plus years. And the short answer is we're still looking. Same with integration sites. I'm getting a little off topic, but it's interesting, I'm sure.
No, it is. So great.
But HIV latency has always been the problem, the reason we don't have a curative therapy. And this is, so as a graduate student, I was thinking about how do we build a therapeutic that can somehow circumvent or overcome this problem. And one idea that I'd float, this is unfortunately the way that these ideas work sometimes is they're not elegant. They're arrived at in very circuitous and inelegant ways. And this is one of those examples. I was thinking that we could try and develop a therapeutic that instead of activating all of the virus, it was an approach called kick and kill that people were very excited about, or shock and kill, activate all or reverse all the latent virus and then kill it with available antiretroviral drugs. Instead of doing that, and the problem was that really did not work and was very toxic in the times that people tried it in patients. We still haven't been able to do that. But instead of trying that, perhaps we could try and find a way to turn off the virus and push it into a latent state, all of it. And then very quickly I realized, well, that would be the same thing as continually taking a drug all the time. You'd just be taking a different drug. But if we maybe had a replicating way or a dynamic way of doing that with perhaps a virus, maybe we could have some sort of parasitic virus that would push the wild type HIV into this latent state continuously.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
What about phages? Anyone identified phages of HIV? What about cultivating those?
And that was basically what this idea came out as.
Sorry to steal the thunder.
No, that's what this ended up being, is a type of parasite of the virus that I didn't know it at the time, but these had been described 60 years before in the 1940s, and I didn't know about them until a few years later. But that was the idea that I basically arrived at as a graduate student, that if we could build a type of phage, it was called a conditionally replicating or a molecular parasite of HIV, then we could do exactly this, and we could suppress the virus or keep the virus load low enough, not necessarily push it into this dormant or latent state, but keep it low enough that it wouldn't cause disease. We would reduce the amount of virus in the blood, and we know that the amount of virus in the blood is directly correlated, still is the single best correlate that we have of disease progression. The lower the amount of virus in the blood, it's called the viral load, the slower an infected person or person living with HIV progresses to AIDS, and the lower the amount of virus in the blood, the lower the viral load, the lower their transmission potential is. For every 1 log or tenfold reduction in viral load, there's about a 2 to 3-fold reduction in transmission potential. So that was the idea.
Well, why? What happens? What do you mean?
Oh, the amount of virus that's circulating for many viruses is the correlate of disease progression. We know this for SARS-CoV-2 as well, that the higher the viral load, the worse the disease is. And transmission is a little easier to explain. Of course, the higher the virus concentration in the blood, that leaks into other compartments, including semen and seminal fluids. And so the lower the viral concentration in those fluids, which translates to lower transmission of the amount of virus burden that's transmitted to the recipient. Does that make sense?
Okay, so what is the protocol again, and how does it work?
So this started off, first I should say, when I was a student, really as mathematical models, as could this work even theoretically? And it turned out that yes, it could work theoretically, but it took 15 years, more than 15 years, to discover one of these parasites, these molecular parasites, and to engineer it so that it would work in monkeys. And that's really the entire story in a nutshell. But I can tell.
In monkeys, was it SIV or was it HIV?
It's SIV. In monkeys, it was SIV. HIV does not infect monkeys, but what we have is a model where an HIV-like virus. So these viruses, these retroviruses, HIV-like retroviruses, are incredibly successful evolutionarily. They've infected every primate on the African continent. And
Well, people have endogenized retroviruses too. I've heard like herbs, right?
Yeah.
Human endogenous then they're, 8% of our DNA are supposedly?
Depending on how you count, it can be up to 11% of our DNA, fragments of retroviral fossils in our genome. But that's correct. We have ancient scars or signatures of retroviral infection in our germlines.
Like placental formation, in gestational mothers, that comes from syncytin, I guess, I may have mispronounced the compound, but that comes from a virus, an endogenized retrovirus, right? Supposedly?
Supposedly, yes, that's correct. HERV-K sync1 is seems to be imported in syncytia formation in placenta, or placental formation. That's absolutely true. This is a newer infection compared to those HERVs or the endogenous retroviruses. These are not necessarily endogenized. These are infectious viruses in African primates. And there's an HIV-like virus that's not endogenized. It's not in the germline. It's transmitting between primates, in every primate essentially. And one of them is in chimpanzees, which is where HIV-1 came from. And another version of this, a cousin, HIV-2, is in a different type of primate called the pseudomangabe. And HIV-2 has also infected humans, but the model that we have in monkeys is that if you take one of these viruses, usually HIV, the HIV-2 or as pseudomangabe version, a version of this, a molecular clone, and infect Asian monkeys, rhesus macaques, who have not been exposed evolutionarily to this virus, they get an AIDS-like disease. And they can die quickly. And that's the model that we used, a version of that model in infants, which is incredibly pathogenic. And these animals succumb to an AIDS-like clinical endpoint in 15 to 17 weeks. So that's the model that we used.
Who is studying latency? I mean, it seems like an incredibly important thing to study. Why is there latency? What governs the period? What factors, govern its the transition into latency or out of latency? Just in this conversation, like I said, phage activity can modulate it, is my guess. Again, extracellular vesicle activity could change. Epigenetic marks could be a pseudo biomarker for viral cells, infected cells. The interplay with the immune system, what kind of cell-to-cell signaling is going on there. We're immune to cell signaling that would, again, push a viral cell into or out of latency. Who studies this?
That's the other part of my laboratory. For the past 15 years, we've studied latency. And there's a subfield of HIV that focuses on latency. We made a number of discoveries in that field and discovered a molecular circuit in the virus, a feedback circuit, regulated by one of the viral proteins called TAT, and really characterized this circuit and showed that it was necessary and sufficient for establishment of viral latency and for the virus to enter or establish, like I said, latency. So there are really three. I can go into that if you like. That's an entirely different part of my laboratory, but
because it comes to mind, and I'm like, wait a minute, what about all this stuff? So if you don't mind,
I would say the phenomenon was discovered in the late 1990s by Bob Silicano at Johns Hopkins, and it was controversial at first because it was discovered at the same time as David Ho, my collaborator before I was a graduate student, published his seminal work about the replication of HIV. And I love telling stories, so I'm just going to tell you a story. You can stop me. It was believed when in the early 1990s, late 1980s, that the reason that patients were not succumbing to AIDS quickly, in most cases, it was usually about 8 to 10 years, the average time that an infected person, that it would take to progress to full-blown AIDS. And the hypothesis in the field was that the virus was sitting dormant for that 8 to 10 years because the technologies really didn't exist. There was no PCR at that time. It was just being invented. The technologies didn't exist to detect the virus at low levels. So David Ho and others employed PCR in the mid-1990s, and also a new set of drugs that were just coming on the market, the protease inhibitors, to very rapidly shut off viral production and measure the viral load with PCR. And they found that there was an enormous amount of viral replication occurring during that pre-AIDS time period of 8 to 10 years. And so the hypothesis shifted based on this data to, it's not that they used something called the bathtub analogy. You can have a low level of water, or viral load in this case, by the tap being off and the drain being stopped up. Or you can have a dynamic equilibrium where the tap is going full blast and the drain is completely open and the water level's low, but it's because there's a lot of turnover, right? And so what Ho and Alan Perelson and others did is they shut off the tap and measured the water level going down, and they found that tap was on full blast. So there were, about 10 to the 9 viral particles being produced per day in an individual. So that
signals when there's a pathology that occurs in somebody that reduces their ability to clear the produced virus. That's when so latency is only a temporary state held up by the person's immune response, I guess.
Okay, so this was the issue, that people thought that latency was not a real thing because David Ho and others had shown that it's really high viral turnover. At about the same time, about a year or two later, Silicano and colleagues published this problem that if you took patients off of drugs, that the virus came roaring back and that they could find virus in resting CD4 T cells, hibernate, essentially dormant. And not many people believed them at first, or at least there were a subset of individuals who did not believe the virus did this. And it took him about 10 years to convince the field. But it's very clear now that the virus is latent. And what's going on is that you don't latency, those, the cells are 1 in a million, 1 in 10 million that are actually dormant or latent. They don't make a difference during active viral replication. They don't have an effect. But as soon as you remove active viral replication with antiretroviral drug regimens, which stop completely viral replication, the only thing left are these dormant cells that are 1 in a million. And if you then discontinue the drugs, the virus comes roaring back from those 1 in a million cells. So
they're kind of like stem cells in a way for a tumor.
Exactly. Yeah, you could think of them that way.
But why some cells, what governs the decision of latency or not, if you can call it such a thing in a given cell? Is it cell type specific or what's going on?
Very good question. And this is what drove the field still drives the field. And I would say, and the way I present it is that there were 3 hypotheses. So the first hypothesis was that the virus integrates randomly into the host genome, pseudo-randomly. It sure likes genes. About 80% of viral integrations are in the 5' end of open reading frames. And of course, genes are 3% of the genome. So it really likes genes, right? But it can go anywhere. You can find it in centromeres, telomeres. You find 80% of it in genes. So the hypothesis was, it must be that there are certain integration sites in the human genome where the virus goes latent. And we've looked at, as a field, tens of thousands, if not hundreds of thousands of latent virus integration sites, searching for these deterministic sites which drive latency. And again, the answer is we're still looking. We're still looking for those sites. No one has found integration sites which are deterministic of latency. You can find cells that are latent that have viruses, full-length intact viral genome integrated inside a fully expressed gene inside of a cell. You can find it in the sense orientation, antisense orientation. You can find it it does not seem to be correlated, as far as we can tell, with integration site. No one has found a good example of that. There are papers, very fancy papers about this, but there's no real answer to those papers. They're just large-scale analyses of atlases of viral integration sites in these patients.
I understand it's not necessarily location specific, but of the various locations that, viruses can be found, can you assess if there's activity going on or if it's just, the virus is just kind of hanging out there? And is it bonded to anything? Is it just free floating? Like, what is its state versus when it's attached to the genome?
No, it's always integrated. I mean, integrated meaning it's insertional mutagenesis. It gets in between 2 base pairs and inserts its 9.7 kb genome in between 2 base pairs. So it's not attached, it's integrated.
Okay, gotcha. So I would suspect there's got to be an epigenetic signature of attachment. Maybe only in the successful areas, but there's got to be. It would alter the reading and transcription of, of the genetic material.
It definitely alters the genetic material, there's no question. Whether the epigenetic marks have any real meaning is still an open question.
Has anyone even looked to see, well, there's more methylation occurring at this site where it endogenized or less or...
Absolutely. Absolutely. 100%. That was a hot area of research for a decade or more. And in fact, one of the main clinical latency reversing agents, they're called latency reversing agents that are used for shock and kill. One of the main clinical candidates were HDAC inhibitors, histone deacetylase inhibitors. And these were tried for at least a decade by many groups and have now effectively been abandoned because reversing methylation or epigenetic chromatin marks does not seem to be an effective way to reverse HIV latency.
What preferential genes appear to be affected by the insertion of HIV? Which ones are impaired or their function is changed or shut off completely?
There's no correlates that people can find for genes that are shut off. If the virus integrates in a specific gene, then that specific gene is of course disrupted. Absolutely. absolutely, but there are two copies of it typically. So the other copy can presumably take over, or the cell dies. But there are no correlates still to this day of specific sites that are determinant of latency that are markers of latently infected cells.
If you were to look at, I don't know how much effort this would take, but if you looked at 100,000 cells or 1 million cells infected by HIV, where would you see these insertions? Is it totally random, or does it appear to follow some kind of patterning? But there's a predominance in certain areas, and on occasion it's in other areas. But
yeah, of course. There are hotspots. There are, as I said, a preponderance. 80% of the integrations are in 5' end of open reading frames. So it likes genes, the integration. But if you look at latent cells that have gone latent or in patients or in culture models, you can't find specific areas or genes that are overrepresented, maybe slightly overrepresented, but I think it's very controversial whether that's a statistical anomaly or real. So no one has an answer to the integration problem, whether virus latency is integration site determined.
Yeah, I can see why, I think, because you have to study more and more cells and more people. So million cell study in 10,000 people affected with HIV, maybe then you would see it, like 3 or 4 avatars or patternings, but it would take a lot to find that, I guess.
That's been done. Maybe not 10,000s of people. Yeah, those sorts of studies have been done. And still, you can find slight preponderances, statistical preponderances that I think most of us are like that. You can find that we've seen that before. So yeah.
What about, maybe a little off topic, but like supposedly right now there's an endogenized retrovirus that's affecting koalas, killing the ones that are, it's like, I guess, was it feral cat? I forget what it is in Australia. The rabbits where a virus had wiped out like 99.5% of them, and then the rest multiplied. But I guess with koalas, same thing is happening or something similar. Any learnings from there, or is it kind of too far afield, that retrovirus?
I've heard about as much as you've heard. I don't know very much about that at all.
Okay. And maybe just something interesting to look at, I guess. Maybe it would give clues to what you're looking at, but maybe not.
It's fascinating. Regardless, back to HIV latency, the second hypothesis was that the virus, we knew that these cells that were latent were resting CD4 T cells, and the hypothesis was that the virus infected, we knew it required, or largely required, activated CD4 T cells. That was the hypothesis. And then maybe these cells relaxed or retreated, and the virus went along for the ride. It was called the epiphenomenon hypothesis. And that was a dominant hypothesis throughout the early 2010s, late 2000 and noughts. And it was a beautiful hypothesis and made a lot of sense. The only problem was there was no evidence testing it, and there was no direct test of it. So we tested that by infecting cells that were activated and letting them turn off using a virus with a very short-lived reporter that would only be expressed but when the virus was expressed. So we turned off the cells in culture and from donors, and cells turned off really readily and really effectively, and the virus didn't seem to care, just kept on going, no matter if the cells were active or the cells were resting. So that was a series of papers, back-to-back papers in 2015 where we showed that, and basically showed that you can't explain the entry to or establishment of latency by the cells, the epiphenomenon hypothesis, and that was subsequently validated by another group, repeating our same experiments in a very similar context. The third hypothesis was that I had been pushing since I was a graduate student, which is that it's not the cells or the integration site, it's actually the virus, and the virus encodes its own program for latency. And this was, I think, very minority opinion, maybe a minority of one. That's what we ultimately showed is certainly one major mechanism of latency establishment, and it's both necessary and sufficient.
So what is this programming? What are the conditions that activate the programming?
It's a very simple virus that has a single promoter. That's 9.7 kb is the entire problem that we have is 9.7 kb in the DNA form. One promoter in the 5' end and called the long terminal repeat. There are two long terminal repeats, one at the 5' end, one at the 3' end, and the promoter is in the 5' long terminal repeat, or LTR, and it drives 9 genes. One promoter drives 9 genes. And it's a very weak promoter. The LTR promoter is exceptionally weak. If you cut it out and drive, say, a GFP off of it, you barely see GFP in 20% of cells. It's super weak. But one of the genes of HIV, TAT, is a transactivator. It's a transcriptional transactivator. And it feeds back onto its own promoter and hyperactivates it. So this forms a positive feedback loop. And what we proposed is that these positive feedback loops we know from engineering are really effective ways to build switches. on-off switches. And maybe what this positive feedback is doing is acting as an on-off switch. And so we characterized that positive feedback loop and how stochastic fluctuations or noise in expression and molecular interactions could act to turn on and off this switch. And that's how, to this day, we believe that latency is established and regulated, that the virus infects a cell, reverse transcribes, inserts its genome randomly, and then TAT is expressed. And if enough TAT is expressed, the feedback loop activates, but it's an incredibly noisy promoter, and these feedback loops amplify those fluctuations. And so you get these enormous fluctuations in the amount of TAT in a cell. They're going up and down. And sometimes these fluctuations are so large that they slam into zero, and that's a molecular extinction event of the TAT molecule. And the promoter can't really recover from that molecular extinction. It doesn't have TAT to activate it anymore. And so that's when these cells can go dormant for HIV, that they don't have enough TAT around to turn them on. And recently, Janssen Pharmaceuticals started developing a latency reversal agent based on our work, TAT, and showed that it was the most effective latency reversing agent that has been demonstrated in the literature to date. This is finally, I mean, it's not, I don't know if it's going to work or not, but it's certainly the most effective LRA that people have reported.
So where are you at in the, are you working on doing a clinical trial for this? Is that monetarily out of reach, or what will be the next step?
We're not. Janssen might be, but we're not involved in that. We're involved in clinical trial for our therapeutic, which is the interfering particle, the tip that was just published. So we got very far afield talking about latency of HIV, but the paper that came out was really about developing one of these interfering particles, or we call them therapeutic interfering particles for HIV.
When is a sweet spot to administer it? I mean, if someone tests positive, but they're still in the initial latency phase or subsequent latency phases, like when would it be best applied?
So the current therapeutic that we just published, that's latency is a sort of a secondary issue for that therapeutic. So we got very far afield talking about latency, but I can go back to the interfering particle, the tip, if you like, and then tell you about administration and when best to administer it.
Yeah, let's do that for the last couple questions.
Yeah. So this, in parallel to working on latency, we were also at the same time working on this very avant-garde idea of building a therapeutic that only needed to be administered once, a single administration therapeutic that could overcome barriers to biodistribution or distribution and could overcome resistance barriers. If it could replicate and only be administered once, it might also have the ability to establish these coevolutionary arms races with the virus, and the virus could not evolve around it. So we were working on that in parallel to the latency work, and finally we're able to develop or discover one of these interfering particles for HIV and engineer it into a efficient interfering particle. By efficient, we had a specific quantitative threshold or engineering optimization criteria that we were going for, which is an R0, or basic reductive ratio of the interfering particle had to be greater than 1, an R0 greater than 1. So we were able to finally discover a defective interfering particle for the virus and engineer it into the therapeutic interfering particle with an R0 greater than 1. And that could be administered in principle at any time during infection, when the virus load is early during infection or during the so-called clinical set point, when the patient is already has an established infection and it has a very high viral load. So the timing of administration in principle shouldn't matter, and that's something we're going to have to test in clinical trials as well.
Well, very good. Leor, where can people keep tabs on your work? What's the best place to go?
I guess.
Do you have a lab website or ResearchGate best, or what's the best place?
There's a lab website. There's a lab Twitter page, Weinberger Lab Twitter page. WeinbergerLab.ucsf.edu is the website. I guess there's some stories in the New York Times by Carl Zimmer. Those would be the best places, yeah.
Thank you for coming.
Well, thank you for your time, Richard, and for the opportunity. Appreciate it.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.